So continuing to think about turning our raw scores into z-scores, same example, same setup from the end of the last clip. Population mean of 30, standard deviation of 8. And now let's say that we're looking at a person who got a raw score of 14 points. Well, what would their z-score equivalent be? If we converted this raw score into the z-score scale, well, 14 is right there. So again, above the mean or below the mean? Below the mean, so its address is negative. And how far below the mean? It is exactly 1, 2 standard deviations, exactly. So let's say -2. Let's do one that doesn't work out quite so simply. Let's say we've got the same distribution and someone has a raw score of 42. Well, we could still probably figure this out without having to reach for calculators and formulas, right? So 42, where is that located? That's located right here. So let's start with what we know. That z-score is for sure going to be positive. So it's more than 1 standard deviation, but less than 2. Well, a full standard deviation, the full distance between these lines is 8 points, always. So it's moved this full distance, but then it moved only to 42. So it was at 38 for 1 standard deviation, and so we know it's going to be at least 1 up there, and then some fraction. So 38, 39, 40 for 142. It went up 4 more points. 4 out of 8 is half. So where did it go? It went up 1.5 standard deviations. Let's do one more example of that. Let's say the raw score we're working with is now a 26. Well, where's the 26 located? That's located in here somewhere. So we know their z-score is going to be negative. So it is exactly 4 points below the mean. 26 to 30 is 4 points of difference. A full standard deviation is 8 points. It moved 4 points, so therefore it only moved half of the distance. Half of a standard deviation. So let's take a look at continuing to work with this. These are, pretty straightforward examples. The idea really here is to be able to understand, put together what the number is with what we're seeing in the graph. But let's do some where we maybe need to use a formula, if you will, get our calculators together. Of course, most of the time, your raw scores aren't going to be these nice, simple whole numbers. So very often in the real world, we're going to need a formula to do this. So to get a z-score with a formula, it's almost the same formula as for a deviation score that I referenced earlier. So the first thing we're going to say is, well, how far is that person's raw score from the mean of raw scores? But we want to put it not in terms of raw points of distance. We want to put it in standard deviations. We want to put the units in standard deviations. So simply, that's what we divide by. Now notice that I put in symbols here, of course, using populations. Population symbols. If I wanted to write the same thing for samples, we just switch the symbols out. So we saw sometimes, once in a while in chapter 4, that whether the data came from a population or a sample, it made a difference mathematically. This isn't one of those cases. So just like computing a mean, the symbols change, but the math doesn't. It's the exact same math. It's really the same formula. We've just swapped out the symbols to denote, are we working with a population or are we working with a sample? So they're fairly interchangeable in terms of mathematics. So that's our simple formula for it. Take the raw score, subtract from it the mean. Again, make sure you're subtracting in the correct order here. If you do mean minus the raw score, you'll get the sign reversed. So this way, if it comes out positive, we know we're above the mean. If it comes out negative, we know we're below the mean. So to work with this, let's consider a version of a problem that we did in lab from chapter 4. One of the problems in chapter 4 that we worked on said If you're in this distribution of scores with this mean and you get a raw score of that, would you rather have the distribution have a standard deviation of 2 points or 8 points? Right? And so what we ended up doing is we put out these graphs and we plugged it all in and saw, oh, well, which one would get me furthest to the right, the highest grade, if you will, for our distribution. Super. Well, we can do that same type of problem. I'm going to change it up a little bit, but that same type of problem. And we could still graph it all out and do it that way, but we could also probably get to the answer faster if we use the formula. So let's say that you have taken some measure and you have a raw score of 56. And we're going to call this a school test, so we want a high performance. We want to get you to the farthest to the right we can get you. So I'm going to give you 3 sets of parameters, 3 sets of means and standard deviations to choose from. Which one would give you the best grade? So let's say in kind of version A of this, the population had a mean of 50, and the standard deviation was 10 points. Now, we could draw the curve, put out the lines, put 50 in the middle, count by tens, and then find that 56 is not quite one standard deviation above the mean, just over half. But the point right now is to work with the formula. Again, you should kind of play with both. It'll help you lock that in. But if we work the formula on this, because we want to know where is that score exactly, we're still on that first purpose. Well, our z-score, our raw score is 56. Our population mean is 50. Standard deviation is 10. So 56 minus 50 is 6. 6 divided by 10. So the z-score equivalent for this is positive 0.60. So it is exactly 61/100ths or 6/10ths of the standard deviation above the mean. How would we describe that performance? We would say that's a pretty common or a typical performance, right? It's in that middle lump. It's between those first 2 standard deviations, one up and one down. Everything in between there is pretty common stuff. So now, let's give you a different option. See if you would like it better. Option B, here we have the population mean is still 50. But in this universe, if you will, the standard deviation is 6. So what I'd like you to do is actually pause the video for a minute, plug that stuff in there, and see what you get. Raw score minus the mean divided by standard deviation. So in this case, you should find that your z-score equivalent is exactly 1. We're exactly 1 standard deviation above the mean. So far, B puts us further to the right, gets us the higher position in the distribution, the better exam performance relative to our classmates, if you will. So let's see what C gives us. Here we're going to change the mean now to 48 points. The standard deviation is 4 points. And again, what's the z-score equivalent here? So 48 minus 50 divided by 4. So, oh, I'm sorry, 56. I don't know, I said 40. 56 minus 48. Woo! Hi, good morning. Caffeine's kicking in. 56 minus 48, then divide by 4, of course. And so here, what you should find is that this raw score within this distribution is 2 standard deviations above the mean. As we'll see, that's pretty far up there. I said the thing goes for infinity, but once you're 2 to 3 standard deviations up, you're really in pretty rare company, if you will. We'll get a better look at that in chapter 6. Anyway, so if this was your exam score, which universe would you prefer to be in? Almost certainly universe C, where you're going to get 2 standard deviations above the mean. So that would be the highest position in the distribution. So we can see it's a pretty simple formula to work with. Just remember that if we don't have all whole numbers like these examples are, always follow our class rounded procedures, round to 2, report your answer rounded to 2 places. Okay, we're going to continue exploring our z-scores in the next clip coming up.